Well, it might appear from our previous work that we've found the key to every door. It might seem like we're on some sort of a Rocky Mountain high, but no, it turns out that if we want to know the convergence of a series, what is the sum of the series? It turns out that using that rule we had earlier, that the series converges if and only if the sequence of partial sums converges, that process is often very, very challenging because determining the rule for the sequence of partial sums is very often extremely tedious at best, and sometimes it's not even really very tenable. And so what we're going to do is find some other ways to get around that issue. So we're going to be able to have, because it turns out that there are certain specific types of series that are of particular use for us. And those particular types of series have some special properties. And because of those properties, it makes determining their convergence easier than finding the sequence of partial sums. So, number one, the definition of convergence of a series. A series converges if the sum is finite. And the theorem says the series converges if and only if the sequence of partial sums converges. However, working with the sequence of partial sums is very often quite a bit of a challenge. We're going to find out some ways, some fulcrums that we can use as for our levers to get over this notion of finding the sequence of partial sums. So there are some special types of series. And so the first special type of series we're going to talk about is the telescoping. By the way, if you have one, it's called a series. If you have more than one, they're called series. It is its own plural. It's like fish. Telescoping. A telescoping series is any series in the form or which can be written or be expressed in the form Bn minus Bn plus 1. You think, well, now what does that look like? Well, we'll see that in just a minute. Let me sort of illustrate what's happening here. Let's expand this and see what happens here. When n equals 1, what do we have? Remember, b is some expression. So when n equals 1, what does this expand out to be? Well, this is b sub 1 minus, when n is 1, this is b sub 2. All right? Plus, when n is 2, this is b sub 2 minus b sub 3. But when n is 3, this is b3 minus b4 plus b4 minus b5, and so on and so on. As a matter of style, do we see this as alternating? Positive, negative, positive, negative, positive, negative. When you before you put the 3 dots, the ellipsis, if it's alternating, you put plus minus to indicate the alternating continuous. That's just a matter of style. So, what do we have here? Well, it's not very hard to see. Look. Boom, 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 boom. The second term here cancels with the first of the next. Is it clear there is no specific number that fails to cancel? When somewhere out here we're going to have plus b50. Well, plus b50 cancels with the subsequent negative b50. And so that will always occur. And so this sum, assuming this works, the sum is b sub 1. So that's a way to think of this. That's the telescoping series. All right? Some specific cases, what would that look like? What we want to do is investigate under what circumstances does this behavior happen, and what are the particulars of that circumstance. So a specific case might look something like this. Suppose we have 2 over, try that again, 3n minus 1 minus 2 over 3n plus 2. All right? So the question is, how do we handle this? Is this what's going on here? Well, with telescoping series, there's a three-step process. Number one, verify telescoping. You first have to check to make sure it actually has this behavior, that it actually is telescoping. And the way that's done is this. To do this, you substitute parenthesis n plus 1 for n in the first term. If you simplify and get the second term, then yes. If you simplify and you don't get the second term, then no. So the question is does this meet the condition for telescoping? So here's what you do. Take the first term, just go off to the side. In place of n, you substitute parenthesis n plus 1. And then you simplify that. Either you will get this or you won't. In this case, this is 3n plus 3 minus 1, which is 2 over 3n plus 2, which is the second term. So, bing, yes, this is a telescoping series. Step one, if you think something is telescoping, you must verify that it is telescoping. If you are given that it is telescoping, then you don't need to do this investigation. You may skip this step if it is explicitly given to be telescoping. If it's not, then you must do that check. If you don't do this check, then your work is not complete and it might not be correct. So, number one, verify that it's telescoping. All right, I'm going to move to number 2, or part B. Part B, we need to compute the limit as n goes to infinity of the second term. I'm going to write that conceptually. More specifically, remember the form is bn minus bn plus 1. It's this term. Forget the negative sign, you don't need it. So we would take the limit as n goes to infinity of b n plus 1. Whatever this second term is, you find that limit. All right? So let's do that for our little problem here. We have verified this is in fact telescoping. Now we take the second term. So we want the limit as n goes to infinity of 2 over 3n plus 2. If that limit is a finite number, then yes, that's good. That's what we want. If that limit is infinite, if this limit is infinite, then this series diverges. If that limit is infinite, then this series diverges. In this particular case, this is not very challenging. Well, this is 2 over infinity, right? As n goes to infinity, 3n goes to infinity. So in our infinity arithmetic, this is 2 over infinity. In our infinity arithmetic, that's 0. So the limit exists. It doesn't need to be 0. It just needs to exist. It needs to be a finite number. And so yes, compute that limit. Yes, that limit is 0. All right? If it does not exist, then this telescoping series diverges. If that limit fails to exist, this series diverges. All right? Now, why might it fail to exist? It might fail to exist because it's positive infinity or negative infinity, or because it oscillates back and forth between two numbers. So if this limit fails to exist, then it is a telescoping series, because we already verified that, but it diverges. If that is a finite number, then it's just so far so good. Bing. If it passes those two requirements, then here's the final result. The sum is b sub n, or I'll say it this way, the first term evaluated at n equals 1. I'll write this, I'm going to need some more space. It's the first term evaluated at n equals 1 minus the limit you just found. Minus the limit you just found. Now that's conceptually, this is horrible mathematics, but conceptually that's what's happening. What really you would do is you would take Bn evaluated at n equals 1 minus the limit as n goes to infinity of Bn plus 1. First term evaluated at 1 minus limit of the second term, the thing we just found in part B. All right? So in our particular case, the sum is, because it did pass A, it did pass B, now we're going to check C. If it fails here, then you don't go on to C. If it fails here, you don't go on even to B. All right? So you must be successful at each stage of the game. And so this sum actually is it's equal to this first piece, 2 over 3n minus 1, evaluated at n equals 1, minus the limit we just found earlier. As you recall, that limit was 0. It's not always 0, but if it is, in this case, it was 0. And so when n equals 1, this is 2 over 3 minus 1 is 2. That's 1. So this sum is 1. This telescoping series converges and the sum is equal to 1. If you're given a telescoping series to work with and you can verify that it is in fact telescoping, and if in fact it does pass condition B, if you have a telescoping series and it passes this condition, then you will always find C. You are struck from here on out. If you're given a telescoping series and you find the telescoping series does converge, then you must find the sum, the end. Anytime you have a converging telescoping series, it is automatically assumed that you will find the sum. And it is you evaluate the first term at n equals 1, and you take the limit of the second term. Essentially, this is a way to conceive of it. You're evaluating the first term at this lower limit n equals 1. You're evaluating the second term at infinity. That's an extremely crude way to think of it, but that's kind of what's going on here. So telescoping series, anything that can be expressed in the form is it's Bn minus Bn plus 1. Anything that can be expressed in that form is a telescoping series. Number one, you must verify, because it might look like it but not be that. So you must verify telescoping. If it does pass that muster, then you compute the limit of the second term, and if that value is finite, then you can actually find the sum.